now we will be looking at the Lab 6 two-stage CMOS op-amp circuit. So we've already analyzed it for part of the pre-lab. Now we're going to put it together in cadence, or not cadence, but LT splice, and make sure it works correctly. So I've already constructed it, so I'll just open it here. We're using the same 1.8K resistor that we've been using. The NMOS and PMOS parameters are all the same. Just make sure W and L are set correctly for every transistor. We've added the M7 and RD resistors here. For the pre-lab, I calculated RD needed to be around 2.4 kilo ohms. We've also added the load capacitor and load resistance as shown. And the supply voltages are plus and minus 5 volts. We're applying a small input. Now the gain's going to be quite high here in this case because we have two stages. So we want to put in a small input signal, in which case I've done 1 millivolt amplitude with a frequency of 1 kilohertz. And the common mode offset voltage is set to 0 because we showed in lab 5 that that's sufficient for a small input signal. If I make this input signal large, then you have to increase VCM. So at 1 kilohertz for 3 periods, you set the simulation time to 3 milliseconds. And my step time is 10 microseconds here. So if we run this, and we plot the input here, that's our 2 millivolts peak to peak. We can plot the output of the first stage, and we can also plot the output of the second stage, either at VO2 or VLOAD. It should look the same. One will just be offset from the other a little bit. So let's plot VO2 and verify that that is close to 0 volts. And it is. It's fairly close. Now it's not perfect. It sits around 0.4 it looks like at DC, but you have to remember that you have to round the value of RD to the nearest value found in the lab. So you could fine tune this by a little bit. Maybe you'd have to decrease that voltage. So you'd have to lower this resistance maybe to 2.3K would have gotten us closer to 0 volts. But 2.3K is not a standard value. And so you wouldn't be able to construct that with a single resistor. You could with series and parallel components, but just a single resistor, 2.4K is probably as good as you're going to get. So I'm going to separate these by right-click, add plot pane, and then I'm just going to kind of drag them to separate them out. And so each stage is inverting. So positive input here leads a negative input out of the first stage, which becomes positive again once you come out the second stage. Again, 2 millivolts peak to peak input, and we can add some little cursor positions so we can figure out what the peak to peak is. Okay. So it looks like the peak to peak output is around 200 millivolts or so, a little over that, 215, which tells us that the total gain is that number divided by 2 millivolts peak to peak input, which is around 105-ish, 107 maybe, which should be pretty close to the pre-lab calculation. And the gain of the first stage should be about the same as it was for lab 5 because we haven't modified that circuit at all. And we can figure out the gain of the second stage by dividing the peak to peak of the red curve by the peak to peak of the blue curve, because we're looking at how much does VO2 change in response to VO1. And so about 200 millivolts here, it looks like VO1 is moving by about 50 millivolts maybe, 50 millivolts. So 200 over 50, the gain's about 4-ish, but you can come up with a better estimate than that when you actually account, get more precision. So lab 6, 2-stage op amp. For this, we need to get a picture of the schematic here. We want to get a picture of the waveforms, like I've shown here, with labeled peak-to-peak values of VO1 and VO2. And we need to also verify the second stage current and DC voltage at the output. So you can kind of approximate that as about 420 millivolts, it looks like. And you can figure out the current just based on Ohm's law. 0.42 minus negative 0.42 minus negative 5 divided by 2400 ohms, or you can directly monitor this current here. And I'll put him on a new plot. I don't think that actually plotted the current. Let's see. Get rid of that. Okay, there's the current. So it looks like it's around 2.255 milliamps. And ideally, you'd expect around 2 milliamps if you have 4 milliamps through M6. So that's pretty close. At least kind of predicts what we would expect. So that's that. So you got the current, Vout DC we measured, and differential gain we also measured. So once you have that, you got your pictures, you can submit this to the Dropbox along with your LT Spice files.